Okay, so let's get started. We're going to be taking a look in this training module at understanding our throttle body data tables within our Gen 3 control module programming. Now, if we've changed out our throttle body from stock to a larger than stock throttle body, we need to update our throttle tables. We'll find that if we don't, we're going to have throttle control error problems. We're going to get IPC wheel torque errors. We're going to get a wrench light on the dash and go into a limp mode and essentially a fail-safe shutdown mode. So we want to understand these tables, what they represent, how the modeling works, and then talk about using some template applicator files that I've provided in our training course folder to be able to account for when you've changed your throttle body. So there's some things between different throttle bodies that are important to understand. Some may have completely different servo motors that open and control the throttle blade. Some will have different throttle position sensors, also need to be accounted for. We don't want to have inaccurate representation of our actual throttle control system. There's a lot of details going on here. So let's just jump in. Let's look at a stock equivalent file. We'll talk about the key areas we need to understand within the modeling, and then we'll talk about bringing some data in here to translate a different throttle body into the programming language for our Gen 3, so everything is going to run smoothly and give us a better starting point. We may need to jump into the table to edit and adjust some things. We will hopefully be able to cover that in future training tutorials. With my demo vehicle, we're going to be putting a supercharger on it, and that's going to be where some of these throttle body tables get out of whack. Because when you're introducing force induction into a model that's based around naturally aspirated operation, we can find that we get some odd behavior out of our throttle control. It's not going to do exactly what Ford's intended. So that's something we'll cover and talk about in another future training tutorial. Let's jump in here and take a look at a stock file and talk about these specific throttle body control tables. What we're going to do is jump into File, Open. Let's go in here to Desktop. Let's go in here to our HPT Gen 3 Coyote Course folder. Let's move down here into our Sample Calibration File subfolder. And then in here, we're going to go ahead and open up a stock equivalent file. I'm going to go up and open up here a 2019 Mustang GT manual stock. And we're going to move in here to our Engine tab. And then we're going to jump in here, General, Airflow, Electric Throttle. Here's where we program all the details associated to the throttle body that we're working with. What I first want to talk about here is the idea behind the throttle body model. That's going to be based on our predicted and effective area tables here. Let's go ahead and open these both up and talk about this a little bit further. We'll close this out so we can see what these look like. Now, what we're going to find here is that we have two tables that are going to be inverses of each other. They're going to be lookups of each other. If we edit one table, we have to edit the other table. Looking at the tables, we're going to find they're based on ETC vacuum. We can see over here as our table lookup on the row or the load axes. Then the top column axis here is going to be based, if we're looking at our predicted table, on effective area. The actual lookup value in the table is going to be our throttle blade opening, and that's going to be in degrees of opening, not going to be in percent. Now, we'll find naturally, as most of the tables here in Ford programming have an inverse, such as our torque and inverse table, same thing's going to go here for our throttle body tables. We'll find we're going to look up in our effective area table here what the ETC vacuum is going to be, what that throttle angle is coming out of our predicted table, and then it'll go ahead and correlate that to an effective area. So we're going to find in this situation that they need to match each other. They're inverses. Now, the way the system is going to work, how do we actually determine what the ETC vacuum is going to be? How do we actually determine the effective area to determine a throttle blade opening? Well, let's peel back the layers on this a little bit just to understand this a little bit more refined and better. Let's base this around this Mustang application. So we'll find that the ETC vacuum is going to be a function coming from our calculated manifold pressure sensor reading. That's a function of our speed density tables as well as our mass airflow. So we translate the mass airflow into a calculated manifold pressure coming through our speed density tables. Now, we've talked about our speed density tables here before, so we know these tables exist. We know this calculator built into the software. We have our speed density calculator that's essentially translating offset, quadratic, and slope terms into this table that we can actually interface and edit for a particular mapped point. So as we're calling out variable cam scheduling, as the cams are moving around, we're translating through the different map points. We have all the tables here associated to different speed density calculations. What comes out of these tables is the calculated manifold pressure on a Mustang. That's fed in here going back in, that is fed into the ETC vacuum. So that's where the ETC vacuum comes from. Now, we also have the translation into the effective area, because obviously the ETC vacuum is coming from mass airflow speed density tables. The effective area here is actually coming from some calculations that go on in the background based on our desired load. So just to run through this real quick, if we go in here to engine and running through our torque modeling here real quick, torque management, driver demand, we have, in this case, driver demand table, Excel pedal versus engine speed. So Excel pedal is where our torque request starts at. It looks up a certain amount of torque that we'd like to see made out of our engine. This is a net torque. This is known as ETC torque request. We can log this within our VCM scanner, and that should translate pretty close to what we see from the driver demand. Now, there are some other tables here, crankshaft compensation, and then there's also other tables for automatic, which is going to be based on the output shaft speed that can tweak and change and multiply what we have coming from our Excel pedal. Thanks for checking out our teaser clip. If you want to see the rest of this video and more than 500 hours of current EFI training we have to offer, make sure you click right here. If you want to go and check out more teaser clips from this training course, click here, and you don't want to miss any of the videos we're going to be releasing on this channel, so make sure you subscribe and click here. Thanks for watching, and I'll see you guys later.